Okay, we've got another exam walkthrough. This is question 20 from Jan 2025 paper on thermodynamics, and this is actually a pretty big question. We have 2 5-markers, both calculations, and they're really interesting as well. So let's just go through them. 50 years ago, Henry Petrie developed a device for the kitchen that produces instant boiling water. A modern version is shown. Okay, the system consists of a small tank connected to a water supply. Water in the tank is heated under pressure to a temperature of 110 degrees. When the water flows out of the tap, so it's heated to 110 degrees, and when it flows out of the tap, it becomes 100 degrees Celsius. Okay, and the water does not boil because it is under pressure. So we make that assumption that the pressure doesn't cause the boiling. It's only because of the heat transfer that occurs as the tank is heated because of a current that flows through it, which comes from the power supply. And the power supply is actually the one that's causing the heating of the tank. Okay, so first let's calculate the power of the power supply, which is P is equals to IV. So I've plugged in the values. 12.6 times 230 volts is going to give me 2,898 watts. And I know E is equals to MC change in T. So this is the energy required to change the temperature. And energy is equals to power times time equals to MC change in T. So I need to find the time, so I will do time is equals to MC change in T over P. So instead of the mass, I'm going to write, so I know density is equals to mass over volume, and mass is equals to density times volume. So density of the water times the volume of tank, which is basically the volume of water that it has, times the specific heat capacity of water, times the change in temperature, divided by the power will give me the time taken to heat the water. So the initial temperature, water enters the tank at 12 degrees Celsius. An electrical heater increases temperature to 110 degrees Celsius. So the temperature goes from 12 degrees Celsius to the temperature which is 110 degrees Celsius. Okay, so I'm not going to plug in all the values. So this is the density of water times the volume of tank times the change in temperature times the specific heat capacity of water divided by the power. So that gives me 423 seconds. So you can just look at the question and just hope you understand it. Okay. Alright, now we're going to be looking at the next question, which says the average rate of energy transfer from the tank to the surroundings is 9.5 watts. A full kettle contains 1.4 times 10 to the power of minus 3 meter cube of water. It takes 180 seconds to bring the full kettle of water to 100 degrees Celsius. And then it says that the kettle is used to bring enough water for 28 cups of tea to 100 degrees Celsius. And it says that a reviewer compared the energy transferred from the tank to the surroundings in 24 hours with the energy transferred by the kettle to make the tea. Okay. The reviewer claimed that the energy transferred from the tank would be greater than the energy transferred by the kettle. Assess the validity of the claim. And they've given us the power of kettle, and they've also given us the volume of 1 cup of tea. It's a bit of a wordplay question, which means you just have to, they want you to use your logic basically. Okay, so there's a lot of tricks here. The question isn't necessarily hard, it's pretty straightforward to the point, but there are just a few tricks here that we have to be careful about. So one kettle, so let's first find this out, okay? We have 1 cup of tea, okay? And it contains 3.5 times 10 to the power of minus 4 meter cube of water. And 1 kettle contains this much volume of water, which we have seen above, right? And so I'm going to put X. How many teacups can I make from 1 full kettle? So 4 cups of tea. Does it make sense? One kettle contains this much of water. Okay, so I'm going to say, okay, this much of water, I have 1.4 times 10 to the power of minus 3 meter cube of water. And I know 1 teacup needs this much amount of water. So how many teacups I can make? So 4 cups of tea from 1 kettle. Okay, now we have the kettle is used to bring enough water for 28 cups. Okay, this is where I think they didn't phrase the question that well, but okay. So for 28 cups, how many kettles do I need? I'm going to put X. So when you cross multiply, you will see that you need 7 kettles. Okay, or you have to heat the water in the kettle 7 times, right? And you have to basically make the kettle full, then put the water in, then make the kettle full, then put the water into the teacups, and you have to do this 7 times basically. Okay, so that's what we are looking at right now. Okay, now it says to bring it takes 180 seconds to bring a full kettle of water to 100 degrees Celsius. Now we're going to calculate the power or the energy that's transferred to the water by 1 kettle with full water, okay, by 1 kettle. So that's going to be 2600 watts times the time taken to heat a full kettle, okay, to heat a full kettle of water with 200 degrees Celsius, and that's going to be 180 seconds. Does it make sense? The energy transferred by 1 kettle to bring water to 100 degrees Celsius, and the kettle is full, it's packed with water, okay. So I'm going to calculate that energy that's transferred by 1 kettle to the water. So that's going to give me 4.68 times 10 to the power of 3 joules. Now this is by 1 kettle. I want for 7 kettles. 7 kettles that are filled with water, and that water is made up to 100 degrees Celsius, right? So I need this much energy to do this process, and I'm going to do it 7 times because I need 7 kettles for 28 cups. So I'm going to times this by 7, and I'm going to get myself energy transferred by 7 kettles is 3.28 times 10 to the power of 6 joules. Okay, now I'm going to calculate the energy that's transferred from the tank to the surroundings in 24 hours. And they've given me 9.5 watts. Okay, so I'm going to take 9.5 watts and I'm going to times it by 24 hours. So 24 hours, let's change that into seconds, 3600. And that's going to be 8.21 times 10 to the power of 5 joules. Okay, now this is the energy that's transferred to the surroundings from the tank in 24 hours. Okay, so we have both the values. Now we just have to see if the person was correct or not. So the person said that the energy transferred from the tank would be greater than the energy transferred by the kettle. The person is wrong because the energy transferred by the kettle is greater. So, not valid claim. Okay, so that's the answer to this question. You can go through both of the questions and I'll show the mark scheme and examiner report as well. So this is the mark scheme. And this is the examiner report.